why is that even a thing? Who was like, let's make kayaks out of concrete and compete? Who came up with that? What's up, guys? Welcome back to my channel, and if you're new here, then welcome to our little corner of the internet. Today we're going to be watching a video titled The Hidden Engineering of Floating Bridges. What even is a floating bridge? Without further ado, let's see what this video is about.
In the early 1900s, Seattle was a growing city hemmed in by geography. To the west was Puget Sound, a vital link to the Pacific Ocean. To the east, Lake Washington stood between the city and the farmland and logging towns of the Cascades. As the population grew, pressure mounted for a reliable east-west transportation route. But Lake Washington wasn't easy to cross.
Wait, is a floating bridge like the type of bridge that's on top of the water that go... Is that even a thing? That's probably not a thing. I don't know.
Carved by glaciers, the lake is deceptively deep, over 200 feet or 60 meters in some places. And under that deep water sits an even deeper problem, a 100-foot layer of soft clay and mud. Building bridge piers all the way to solid ground would have required staggeringly sized supports. The cost and complexity made it infeasible to even consider. But in 1921, an engineer named Homer Hadley proposed something radical, a bridge that didn't rest on the bottom at all. Instead, it would float on massive hollow concrete pontoons, riding on the surface like a ship. It took nearly 2 decades for his idea to gain traction, but with the New Deal and Public Works Administration, new possibilities for transportation routes across the country began to open up. Federal funds flowed, and construction finally began on what would become the Lacey V. Murrow Bridge. When it opened in 1940, it was the first floating concrete highway of its kind, a marvel of engineering and a symbol of ingenuity under constraint. But floating bridge.
So it is a floating bridge, but it looks so solid. And concrete weighs a lot. Concrete sinks to the bottom. What? Oh, that's why we're watching the engineering of it, huh? I don't understand.
Bridges, by their nature, carry some unique vulnerabilities. And 50 years later, this span would be swallowed by the very lake it crossed. Between that time and since, the Seattle area has kind of become the floating concrete highway capital of the world. That's not an official designation, at least not yet, but there aren't that many of these structures around the globe. And you
know when you see someone who's like really enthusiastic about something, and it makes you want to learn about it because he looks like he's very enthusiastic about this. And he looks very happy. It's just, you can't help but get happy yourself and be like, you know, I love it.
At least not yet, but there aren't that many of these structures around the globe. And 4 of the 5 longest ones on Earth are clustered in one small area of Washington state. You have Hood Canal, Evergreen Point, Lacey V. Murrow, and its neighbor, the Homer M. Hadley Memorial Bridge, named for the engineer who floated the idea in the first place. Washington has had some high-profile failures, but also some remarkable successes, including a test for light rail transit over a floating bridge just last month in June 2025. It's a niche branch of engineering full of creative solutions and unexpected stories, so I want to take you on a little tour of the hidden engineering behind them. I'm Grady, and this is Practical Engineering. Floating bridges are basically as old as recorded history. It's not a complicated idea. Place pontoons across a body of water, then span them with a deck.
This is the type of bridge that I was talking about, the ones that go, you know, they move with the waves. So scary. This also somehow reminded me of like the fact that I don't know if you guys knew, but if you sink in a car, you have to open the window, you know, roll down your window. Well, nowadays you don't roll it, and that's where I'm getting to. But you have to roll down your window to get out of the car, because if you try to open the door while underwater, it fills with water, and then, well, you can't really open the door because, you know, water. But now with electric cars, if your car is sinking, how can you open the window if like the electricity of the car fails? And then you'd just be stuck in the car in the bottom of a lake. But yeah, that's not what this video is about.
Thousands of years, this straightforward solution has provided a fast and efficient way to cross rivers and lakes, particularly in cases where permanent bridges were impractical or when the need for a crossing was urgent. In fact, floating bridges have been most widely used in military applications, going all the way back to Xerxes crossing the Dardanelles in 480 BCE. They can be made portable, quick to erect, flexible to a wide variety of situations, and they generally don't require a lot of heavy equipment. There are countless designs that have been used worldwide in various military engagements.
Whoa.
But most floating bridges, both ancient and modern, weren't meant to last. They're quick to put up, but also quick to take out, either on purpose or by Mother Nature. They provide the means to get in, get across, and get out, so they aren't usually designed for extreme conditions. Transitioning from temporary military crossings to permanent infrastructure was a massive leap, and it brought with it a host of engineering challenges. An obvious one is navigation. A bridge that floats on the surface of the water is, by default, a barrier to boats. So permanent floating bridges need to make room for maritime traffic. Designers have solved this in several ways, and Washington State offers a few good case studies. The Evergreen Point floating bridge includes elevated approach spans on either end, allowing ships to pass beneath before the road descends to water level. The original Lacey v. Murrow Bridge took a different approach. Near its center, a retractable span could be pulled into a pocket formed by adjacent pontoons, opening a navigable channel. But not only did the movable span create interruptions to vehicle traffic on the busy highway, it also created awkward roadway curves that caused frequent accidents. The
Okay, but how does it work though? How does it float?
mechanism was eventually removed after the East Channel Bridge was replaced to increase its vertical clearance, providing boats with an alternative route between the two sides of Lake Washington. Further west, the Hood Canal Bridge incorporates truss spans for smaller craft, and it has hydraulic lift sections for larger ships. The U.S. Naval Base Kitsap is not far away, so sometimes the bridge even has to open for Navy submarines. These movable spans can raise vertically above the pontoons, while adjacent bridge segments slide back underneath. The system is flexible. One side can be open for tall but narrow vessels, or both for wider ships. But floating bridges don't just have to make room for boats. In a sense, they are boats. Many historical spans literally floated on boats lashed together, and that comes with its own complications. Unlike fixed structures, floating
That's kind of cool. That's kind of cool.
bridges are constantly interacting with water, waves, currents, and sometimes even tides and ice. They're easiest to implement on calm lakes or rivers with minimal flooding, but water is water, and it's a totally different type of engineering when you're not counting on firm ground to keep things in place. We don't just stretch floating bridges across the banks and hope for the best. They're actually moored in place, usually by long cables and anchors, to keep materials from overstressing and prevent movements that would make the roadway uncomfortable or dangerous.
True.
Some anchors use massive concrete slabs placed on the lake bed. Others are tied to piles driven deep into the ground. In particular,
But, I mean, it's still floating, yeah.
deep water or soft soil, anchors are lowered to the bottom with water hoses that jet soil away, allowing the anchor to sink deep into the mud. These anchoring systems do double duty, providing both structural integrity and day-to-day safety for drivers. But even with
Right, I didn't even think about that, because if you just put a floating bridge on top of water and there's tides and it starts moving, then it cracks. So you can't. But then but what if it's, well, I guess it's placed in a place where there's not a lot of wave action. But then it technically is not floating. I mean, technically it is floating, but it's not floating on top of the water, if that makes sense. Or it is, but at the same time, it's kind of not.
them, floating bridges have some unique challenges. They naturally sit low to the water, which means that in high winds, waves can crash directly
Yes.
onto the roadway, obscuring the visibility and creating serious risks to road users. Motion from waves and wind can also cause the bridge to flex and shift beneath vehicles, especially unnerving for drivers unused to the sensation. In Washington state, all the major floating bridges have been closed at various times due to weather. The DOT enforces wind thresholds for each bridge. If the wind exceeds the threshold, the bridge is closed to traffic.
See, basically, if it was actually floating on top of the water there, it would move with the waves. But it doesn't because it's anchored to the lake bed, which kind of makes it like it's floating in the air with the force of water. Does that make sense?
Even if the bridge is structurally sound, these closures reflect the reality that in extreme weather, the bridge itself becomes part of the storm. But we still haven't addressed the floating elephant in the pool here, the concrete pontoons themselves. Floating bridges have traditionally been made of wood or inflatable rubber, which makes sense if you're trying to stay light and portable, but permanent infrastructure demands something more durable. It might seem counterintuitive to build a buoyant structure out of concrete, but it's not as crazy as it sounds. In fact, civil engineering students compete every year in concrete canoe races hosted by the American Society of Civil Engineers. Actually, I was doing a little recreational math to find a way to make this intuitive, and I stumbled upon a fun little fact.
Why is that even a thing? Who was like, let's make kayaks out of concrete and compete? Who came up with that?
If you want to build a neutrally buoyant, hollow concrete cube, there's a neat rule of thumb you can use. Just take the wall thickness in inches, and that's your outer dimension in feet. Want 12-inch thick concrete walls? You'll need a roughly 12-foot cube. This is only fun because of the imperial system, obviously. It's less exciting to say that the two dimensions have a roughly linear relationship with a factor of 12. And I guess it's not really that useful, except that it helps visualize just how feasible it is to make concrete float. Of course, real pontoons have to do more than just barely float themselves. They have to carry the weight of a deck and whatever crosses it with an acceptable margin of safety. That means they're built much larger than a neutrally buoyant box, but mass isn't the only issue. Concrete is a reliable material, and if you watch the channel for a while, you know there are a few things you can count on concrete to do, and one of them is to crack. Usually not a big deal for a lot of structures, but that's a pretty big problem if you're trying to keep water out of a pontoon. Designers put enormous effort into preventing leaks. Modern pontoons are subdivided into sealed chambers. Watertight doors are installed between the chambers so they can still be accessed and inspected. Leak detection systems provide early warnings if anything goes wrong, and piping is pre-installed with pumps on standby, so if a leak develops, the chambers can be pumped dry before disaster strikes. The concrete recipe itself gets extra attention.
That's
Specialized
crazy.
mixes reduce shrinkage, improve water resistance, and resist abrasion. Even temperature control during curing matters. For the replacement of the Evergreen Point Bridge, contractors embedded heating pipes in the base slabs of the pontoons, allowing them to match the temperature of the walls as they were cast. This enabled the entire structure to cool down at a uniform rate, reducing thermal stresses that could lead to cracking. There were also errors during construction, though. A flaw in the post-tensioning system led to millions of dollars in change orders halfway through construction and delayed the project significantly while they worked out a repair. But there's a good reason why they were so careful to get the designs right on that project. Of the 4 floating bridges,
Why wouldn't you just make it out of, I don't know, plastic? Or something else? Why concrete?
in Washington state,
Or, well, you couldn't use wood really because it would rot, but
2 of them have sunk. In February 1979, a severe storm caused the western half of the Hood Canal Bridge to lose its buoyancy. Investigations revealed that open hatches allowed rain and waves to blow in, slowly filling the pontoons and ultimately leading to the western half of the bridge sinking. The DOT had to establish a temporary ferry service across the canal for nearly 4 years while the western span was rebuilt.
wow.
Then in 1990, it happened again. This time the failure occurred during rehabilitation work on the Lacey v. Murrow Bridge while it was closed. Contractors were using hydro-demolition, high-pressure water jets, to remove old concrete from the road deck. Because the water was considered contaminated, it had to be stored rather than released into Lake Washington. Engineers calculated that the pontoon chambers could hold the runoff safely. To accommodate that, they removed the watertight doors that normally separated the internal compartments. But when a storm hit over Thanksgiving weekend, water flooded into the open chambers. The bridge partially sank, severing cables on the adjacent Hadley Bridge and delaying the project by more than a year. A potent reminder that even small design or operational oversights can have major consequences on this type of structure. And we still have a lot to learn. Recently, Sound Transit began testing light.
Usually when I watch these though, like I get scared of using, like, for example, skyscrapers. When I heard of the engineer of skyscrapers, I was like, I'm never gonna go on a skyscraper ever. Like, that's just like, redefines gravity. Defies gravity. But this seems pretty solid. If there is no storms or no nothing, it seems like a very, very solid engineering.
We still have a lot to learn. Recently, Sound Transit began testing light rail trains on the Homer-Hadley Bridge, introducing a whole new set of engineering puzzles. One is electricity. With power running through the rails, there was a concern about stray currents damaging the bridge. To prevent this, the track is mounted on insulated blocks with drip caps to prevent water from creating a conductive path. And then there's bridge movement. Unlike typical bridges, a floating bridge can roll, pitch, and yaw with weather, lake level, and traffic loads. The joints between the fixed shoreline and the bridge have to be able to accommodate movement. It's usually not an issue for cars, trucks, bikes, or pedestrians, but trains require very precise track alignment. Engineers had to develop an innovative track bridge system. It uses specialized bearings to distribute every kind of movement over a longer distance, keeping tracks aligned even as the floating structure shifts beneath it. Testing in June went well, but there's more to be done before you can ride the Link Light Rail across a floating highway. If floating bridges are the present, floating tunnels might be the future. I talked about immersed tube tunnels in a previous video. They're used around the world, made by lowering precast sections to the seafloor and connecting them underwater. But what if, instead of resting on the bottom, those tunnels floated in the water column? It should be possible to suspend a tunnel with negative buoyancy using surface pontoons, or even
Why would you ever do that?
Another one with positive buoyancy to the bottom using anchors. In deep water, this could dramatically shorten tunnel lengths, reduce excavation costs, and minimize environmental impacts.
Oh.
Norway has actually proposed such a tunnel across a fjord on its western coast, a project that, if realized, would be the first of its kind. Like floating bridges before it, this tunnel will face a long list of unknowns. But that's the essence of engineering,
crazy.
Meeting each challenge with solutions tailored to a specific place and need. There aren't many locations where floating infrastructure makes sense. The conditions have to be just right. Calm waters, minimal ice, manageable tides. But where the conditions do allow, floating bridges and their hopefully future descendants open up new possibilities for connection, mobility, and engineering. While we're talking about bridges and maritime traffic, I wanted to mention that the Key Bridge is back in the news. NTSB is still working on the investigation, but they recently released a recommendations report. In my video on the collapse, I described how engineers evaluate a bridge's vulnerability to vessel collisions. NTSB went through the same math and found that the risk to the Key Bridge was about 30 times higher than the minimum requirements for new bridges. They're recommending that owners of 68 bridges across the country do this exercise. If you want to make headlines, that's how you do it. When it came out, the story was reported across the US by more than 240 news sources with a good mix of left, center, and right-leaning sources. Today's sponsor, Ground News, makes it easy to see them all in one place, but more than that, it adds context to help you consider any biases in the reporting. Let me know what you think.
Do we have any engineers in the chat? I've always said that if I wasn't a YouTuber, I'd love to be what is it when the people who like dig down and like find pieces and are like, wow, this is part of history. Archaeologist. It's not archaeologist, I know, but I don't know how to say the word. But engineering seems like such an interesting thing too, because you get to kind of create new ways. And, you know, I don't know, it seems like a very interesting job to have. But yeah, this was a really, really interesting video. I have never seen a floating bridge in my life, but now I kind of want to go and see one. It would be nice to drive over this. It's a bit of a weird concept, but I like it. Thank you guys for joining me for this video. I really hope you enjoyed it. Please leave a like, subscribe if you haven't yet, and I'll see you guys in the next video. Bye!